Welcome to this presentation. It's a tutorial. And so the goal of this tutorial is not only to give you some insights into recent developments in computer vision, but also to give you some of the technical background. So I actually hope that you will learn a little bit about how we actually solve the problems that we have in computer vision. If there's anything that's not clear in my talk, feel free to just raise your hand, interrupt me at any given time. And I think this is important. If you don't understand something, very likely your neighbor doesn't understand it either. And then if you ask the question, things will become clearer. Okay, that's said up front. Some more information about myself. I'm heading the computer vision lab or group in Munich. The group has grown quite considerably since I started in Munich about 6 years ago. We have now about 25 PhD students and about 5 postdocs from many different countries. We've even had PhD students from Korea as well. So if you don't have a PhD yet and you're considering maybe doing a PhD, reach out to us, and you know, we are always looking for talented people in this area. Computer vision is a very popular area. I started computer vision almost 20 years ago. At the time, it was not very popular. It was a niche area in computer science, but it's grown a lot in popularity, partially due to the advances in consumer electronics. That you have now smartphones with cameras on them, that you can put lots of cameras in cars as well. And so we, you know, every day I open the newspaper and there's some article about my research area. That wasn't the case 10 years ago, but now you see articles about self-driving cars, about 3D reconstruction from images. So all of this is becoming popular. One of the most popular and classical challenges in computer vision is the reconstruction of the world from images. And this is a problem that you're all familiar with. We walk around the world. We constantly see and observe the world through our eyes, but what we see are only two-dimensional projections of the 3D world, and one of the challenges is that we want to actually recover the 3D structure from these 2D images. When I say recover the 3D structure, and when people talk about 3D reconstruction, there is not a clear definition of what that actually means. Typically, when someone says, I want this or that, you have to really be precise. What do you mean by 3D reconstruction? Typically, for example, in computer vision, when people talk about 3D reconstruction, they mean some point cloud. What I mean in this setting is actually a dense reconstruction. I want to recover a dense surface that represents the geometry of the structure. And that's a very different problem from just a point cloud. The key difference is that from a mathematical point of view, this dense reconstruction is an example of an infinite dimensional problem. Why is that? You know, typically when you talk about dimensions in the public, somehow people get scared. The more dimensions, the scarier. I'm not sure why that is, because it's really nothing scary about dimensions. Here it's infinite dimensional. What does that mean? Let's say we take a wild guess at what's in front of the camera, a sphere. And then we start perturbing that sphere at all its points, say in the normal direction. What we get are new geometric configurations. And each of these points along the sphere is a degree of freedom to our shape optimization problem. And since the sphere has infinitely many points, there is your infinitely many degrees of freedom. And that's important. What it means in practice is that the space of conceivable solutions is very large. The space of all possible 3D reconstructions is huge. Even if you discretize space into lots of little voxels, each voxel can be object or background. And so you're going to have combinatorially many possible configurations of object background. If you have n voxels, then the number of possible, reconstructions is 2 to the power of n. And n is usually large, so in practice it means we cannot try all reconstructions to see which one best matches the observations. So what do? We have to tackle this somehow smarter. What I'm going to talk about now is the so-called variational methods. This is a class of optimization techniques that are very popular in computer vision and that actually allow to solve a number of classical problems to what I think is currently the best techniques around today. I will talk about relations to learning inference. I will focus then on that image-based reconstruction problem, super resolution texturing, and lastly I'll come to reconstructions, 3D reconstructions in space and time. Variational methods is not a recent thing. It's actually very old, and I think if you want to trace back variational methods to their origins, you end up with a problem of this type. I'm sure you've seen this kind of structure before. Has anyone seen this in a science museum, maybe? I guess you have. So there's typically, you have 4 different trajectories in this case, and what you're supposed to do, and this is popular with kids, they place these balls here, and then they let them roll down the various passes. And the question here that you can ask is, which one is the fastest? Which one gets me from A to B in the fastest way? Note, it's not the shortest path. We all know the shortest path is the straight line. It's the path that has a minimum runtime. So let's take a vote here. Who thinks that this is the shortest path, the upper one here? No one. Very good. Who thinks the straight line is the shortest runtime? Some people. Who thinks this third one is the fastest runtime? And who thinks the last one is the fastest? And who has not decided? Quite a lot. Okay, I guess after this you probably want the answer. The answer is I don't actually know. I didn't try it myself, I didn't do the calculation, so I cannot really say which one is going to give you the fastest runtime, but I think it's definitely one of these lower 2. This problem is just a simple version of a more challenging problem. The more challenging problem is not to choose among these 4 possible passes which one gives the shortest runtime. The question is, if you could design your own path, which one would you design? Which one would get you there fastest? And this is again an infinite dimensional problem. Why is that? Let's take this as the x-axis here, and then we have for each x we have a height here, and we can choose the height for every x differently, and that represents all possible passes. And then we have to find the optimal height for each x. That is an infinite dimensional problem again, because we have infinitely many degrees of freedom to modify the path, and we want to find the shortest, the one that gives the shortest runtime. This is a problem that was first solved by a mathematician by the name of Johann Bernoulli. If you know your history, you will know there's a whole dynasty of Bernoullis, mathematicians, Swiss mathematicians. I believe Johann is probably the most famous of them all. And this is his solution. And I think there are 2 things to note about this solution. First of all, the date is written here, 1697. So this, you could say, is maybe the origin of the variational methods, because this was one of the first non-trivial variational problems that was solved in the 17th century. That's how far back these techniques go. The second thing to note, however, is that the solutions were very, very graphical. He must have constructed the optimal path geometrically, with a lot of drawings. Whereas what we use nowadays is a more formalized version of variational methods that was pioneered by people like Euler and Lagrange, a lot of other famous mathematicians. The idea of variational methods is quite simple. You take your solution space, let's say here this 2-dimensional space, you assign a cost to each solution. For example, the runtime from A to B. Once you have a physical model of the ball, you can compute the runtime. And then you can say, now find the path, the configuration in that space with the lowest cost, the lowest runtime, for example. And here in this 2D plot, it would be somewhere here, the configuration of lowest cost. But you already see one difficulty. Even in this 2D solution space, how do I find the configuration of lowest energy? Of course, you can discretize your space, like on this grid you see here, and then try all solutions, take the one with lowest cost. That's a technique that always works. It's extremely naive. It's called the complete search. It's naive, but there are sometimes problems where you cannot beat the complete search. In particular, if the problems are low dimensional, here it's 2 dimensions, and if the evaluation of the cost can be done fast, then you can try everything. Once the evaluation of the cost is involved, and once the dimension of the problem is not 2, but 3, 4, 5, 6, at some point, obviously this approach breaks down, because the space of conceivable solutions on this discretized lattice grows exponentially with the number of dimensions. And so this is not a technique that is popular to use for 3D reconstruction. It's not going to work. Here are some examples of variational methods in image analysis, and I apologize for those who don't have the right, say, mathematical background, but I try to keep the number of equations and formulas a bit limited so as to not overload everyone here. This is a problem of image denoising. This is where a lot of variational methods became popular in image analysis. The idea is that you have an image, f is the image, x is the pixel coordinate, and so f of x is the brightness at every pixel. And then you want to approximate f, so you set up with something that is smooth, spatially smooth. This is the challenge, and so you set up a cost function that has typically 2 terms. One is called a data term, one is called a regularization or smoothness term, and indeed one measures how close is u, the desired solution, to the observation f, here in the least squares kind of sense. And the second term tells us how smooth is u. What we do is we basically have a cost that penalizes the gradients, the derivative of u, the changes of u, of the brightness when moving from one pixel to the other. So the idea is that you have some input image that may be noisy, and then you have some denoised version that you obtain by minimizing this cost function. So we typically have these kinds of cost functions, and then this is something you all remember from high school mathematics. You can say the minimum is attained once the derivative is 0. Right? So the idea is that if this is my cost as a function of u, then at the minimum I have a horizontal tangent, it's 0 derivative. This is of course for differentiable energies. We'll only consider these for now. Of course, once you remember more about high school mathematics, you will know that this could also be 0 at a local minimum. It could be 0 at maxima and even at saddle points. In other words, this is a necessary condition, but it's typically not a sufficient condition, unless your cost function is convex. Once your cost is convex, then it's also a sufficient condition, which is nice because it means once we solve this equation, we have the optimum. But before we actually solve it, there is one caveat, one challenge, and that is, in some sense, this picture is misleading. I was always telling you from the start that the solution spaces are infinite dimensional. So they're certainly not one-dimensional. In that sense, this is an abstract drawing, but the space of solutions here actually has infinitely many directions and degrees of freedom. So the question becomes, how can I actually define derivatives with respect to u when u is not a scalar but a function? And this is there are many ways to introduce these functional derivatives. One that I like in particular was introduced by a French mathematician by the name of Gateaux around the beginning of the 20th century. This is the so-called Gateaux derivative. And I want to derive that here for you to actually see how this works. It's not very difficult. The idea is we have a cost. Typically, it's a cost that depends on some function u, and maybe its derivative. So u prime is the spatial derivative of u, x is the space coordinate, and omega is the domain where u is defined. Some cost doesn't really matter what the cost is, and now we want to define derivatives, and as you may remember from high school math, you can also introduce directional derivatives, the change of E with U in direction h. So h is some direction in space. How do I define it? I measure the energy at U plus some offset epsilon h minus E at the original location U. I divide by epsilon and let epsilon go to 0. Very classical definition of derivative. Now we can introduce this form in here. And so the idea here is that if this is a function u, maybe the initial one, then we add a little perturbation of u at some, maybe localized, doesn't have to be localized, that depends on h, but a little perturbation, and we want to check how does the energy change if we add a little bit of variation on the path, for example, the shortest path problem that I started with. So once we enter this definition in here, we get this form. And then, since epsilon tends to 0 here, we can do a Taylor expansion in epsilon h, and also in the second argument here. And so then we get L of u and u prime, epsilon h, the perturbation, times dl by du, and epsilon h prime times dl by du prime. And then minus L here. So the L's cancel. In addition, the epsilons here cancel. And you notice I actually explicitly omitted the higher order terms in the Taylor expansion because they all have epsilon squared, so they will vanish in the limit anyway. And so what remains once we carry out the limit is just dl by du times h plus h prime times dl by du prime. So this is the directional derivative in h, and as you may recall, what we can do now is we can do integration by parts. H prime is dh by dx, so we can move the derivative of h onto the second term here, and then we get a minus sign, and we can pull out the h here. So we have h times dl by du minus ddx h dl by du prime. And this is omitting boundary terms. What I'm assuming now is that the perturbation h is 0 on the boundary. This is called the Dirichlet boundary condition. There are others, but I'll not go into too much detail here. It's not so important. Basically, what we can now deduce is from this calculation, we can deduce the definition of the functional gradient. Basically, the functional gradient is the expression with which I multiply h to get the directional derivative in h. This is something you also know from finite dimensional analysis, that the directional derivative in some direction is given by the gradient projected onto that direction. And that's exactly what we have here. And so, in other words, we can deduce that the functional derivative is actually given by this expression in blue here, dl du minus ddx dl du prime. And the necessary optimality condition is then just stating that this expression should be 0. And this is called the Euler-Lagrange equation. For those who have not heard it, maybe some of you have heard it, I don't know. The Euler-Lagrange equation is a core ingredient in variational methods. This is the extremality condition for this functional calculus. It's a typically partial differential equation, and so invariably anyone who works on variational methods typically also works on partial differential equations, because once you solve the variational problem, you're usually faced with solving differential equations. Again, here the idea being that at the minimum this should be 0. So this is this necessary condition. Here are the two guys who coined the name, Euler and Lagrange. Obviously they lived before Gateaux, so they didn't actually use Gateaux's way of deriving it. They had other ways of deriving it, but they pioneered and coined the name here. For those who don't know Euler and Lagrange, then I really can't help you. These are two of the most famous mathematicians in the history of mankind. So we have this extremality condition given by the Euler-Lagrange equation. It's a partial differential equation. In general, these equations are not easy to solve. It's not obvious if you get given an unknown equation how you find a solution. There is one very popular strategy, and this is a technique called gradient descent, and it basically means you start with an initial configuration, say u0 of x, and then you perturb that configuration in time, so you add a time domain, a time variable, and in time you perturb it in the direction of the negative gradient. The idea being, this is sometimes called steepest descent, you just put yourself in that energy landscape and you just go downhill. At every step you check what is the steepest way down, which direction decreases the energy most, and that's this one, the negative gradient, and then you go in exactly that direction over time. This is an iterative approach, and it works fairly well. It gives you a local minimum. And this is nice because it's applicable to any energy provided that it's differentiable. Of course, it will typically only give you a local minimum. If your energy is convex, that's, as I said, sufficient to get the optimum. But one should say the gradient descent may not be the fastest algorithm. There are often more efficient algorithms nowadays that, for example, primal dual algorithms and other types of ADMM algorithms that get you to the minimum faster, but they're all somehow related to the gradient descent. Here, once I enter this functional gradient, this is what I get with this L. I didn't say what L was. L is this Lagrange. It's called the Lagrange density often. So here, for example, L is the integrand here for the energy. We considered this smoothing with a quadratic data term, now a quadratic smoothness term. Once we insert that in here, we get this equation. So this is the equation where we start from an initial image, typically the input image. Once we run the gradient descent, we get a denoised version of the image. This gradient descent is interesting. It's called a diffusion equation. In particular, the second part here is the diffusion term. Diffusion is when the derivative in time is proportional to the second derivative in space. This is called a diffusion process, something that's studied frequently in physics. And one of the things that's known, for example, for this so-called Dirichlet energy, the quadratic smoothness energy, once you do a gradient descent, what you get is a sequence of Gaussian blurred input images. And so once we run this gradient descent, here is what we get. Things get more and more blurry, and typically the audience is not really blown away by this result. It's a result that everyone knows. When you have an image that's defocused, you get this kind of blurring as well. But here's something, a slight modification of this original problem, and this is a modification which is often accredited to Rudin, Osher, and Fatemi, and this is they drop the square here. Why would you drop the square? You want something that is smooth, but you want to preserve discontinuity. So you don't want to blur everything. You want to remove the noise, but you don't want to remove sharp edges in the original image. And once you drop the square, you have a better chance of preserving jumps, because the quadratic energy will suppress any jump in this function u, whereas if I just penalize it linearly, then I have a tendency of preserving jumps. And this is called the total variation, and the Rudin, Osher, Fatemi paper is one that really popularized it. There are some earlier versions of the total variation, for example, used in the 80s for optical flow estimation. But typically, one can say a lot of this research on these adaptive variational techniques was started in the late 80s and 90s. Here's the gradient descent. What you get is again a diffusion term here. This is the more general diffusion, and now you have a diffusivity G that tells you how fast does my brightness or diffuse, and this diffusivity depends on the gradient, as you see, in a way that if the gradient is strong, I have a small diffusivity, meaning the brightnesses don't diffuse as fast in strong gradient areas. This is called a nonlinear diffusion because the diffusivity actually depends on U. And this was popularized, one of the first nonlinear, actually I think the first nonlinear diffusion for image denoising was proposed by Perona and Malik in 1990. And then this one is the Rudin Osher Fatemi one. There's also matrix valued anisotropic diffusions that were pioneered by people like Joachim Weikert. Here's a comparison. This is the linear diffusion. Things get blurred, everything disappears, the noise disappears, the signal disappears along with the noise. Here's the nonlinear diffusion. And you see something very interesting. You see that fine-scale structures like the hair, etc., disappear, whereas the shoulder line here is still very sharply visible. And so this is a process that removes noise but tends to preserve certain aspects of the signal, in particular edges. And so it was a very popular technique for edge detection in the 90s. So this is the idea of variational methods, and I hope I conveyed you a little bit that you have a cost function, you compute the Euler-Lagrange equation, the gradient descent, and I hope I also convinced you that if you just change the cost function a tiny little bit, you get a very different solution. Cost functions are one way of looking at it. There are many other ways, and typically optimization is a paradigm that's really popular in image analysis and in many areas of sciences. One of the things it relates to is statistical inference, where often you also maximize some probability distribution. And this is something where it relates to the aspect of prior knowledge. And so I wanted to talk a little bit about that in the context of segmentation. I don't know if anyone has seen this image before. If you have not seen it, what you're supposed to see on this image is a dog, a Dalmatian dog, which has the head in the grass here with the ear here and the muzzle here, and then the front legs are here and the hind legs are somewhere here. So it's kind of facing away from the viewer. I don't know how well any people can see the dog. What you're solving here as a human, when you actually determine where is the dog and where is the background, is a problem called image segmentation or figure ground segregation. There are many different terms for it. Another very popular shape optimization problem in image analysis. But one of the things to note here is when humans do image segmentation, they use knowledge about the world. They use the fact that they've seen Dalmatian dogs before. People who have never seen a Dalmatian dog will typically not be able to do the segmentation here. Meaning we use prior knowledge, and the question is, can we do that in a machine as well? Here's another nasty example. I'm sure no one sees anything, as this is a very noisy image, but let me show you once I run this. It's actually a video. You can probably see there's a walking person here. I generated this video artificially. I started from a real video and explicitly added so much noise to make it very difficult for you to actually see the person. So it's not an easy problem even for humans to determine where's the object. In fact, anytime you stop the video, you hardly see anything. If I stop the video in between, you almost instantly lose the object. So the question is, if we give a machine this sequence, and if we tell the machine what humans look like, how they walk, can we teach a computer to actually track that person? The first question is, once I say person and segment or track the person, what do I mean? I want to actually find the silhouette of the person. So the question is, how do I represent silhouettes? This is one popular way. It's called the sign distance function, used in the so-called level set methods. The idea is, if this is the image plane, then you can represent any curve, any closed curve, be it simply connected or not. You can represent it as the zero level of some height function, the gray value shaded function, and this is what we call phi. And the idea of level set methods is now, rather than actually propagating the points of the boundary as points, we evolve that embedding function over time and just read out the zero level at any given time. And this can be done for image segmentation. This was done, for example, by Chan and Wese. Here's their method. And you see nicely how you can segment multiple objects. You don't really have to specify how many objects there are. And you can track people, and here I added this bar to make things a little bit more difficult, so the person is behind this artificially added occlusion. And you see what happens is this Chan-Wese method separates bright and dark, and in addition there is some regularity term that says the boundary should not be too long. But still the shadow is often part of the segmentation, something that we humans tend to not even see. I was first surprised when I saw the results, and then I realized, yes, indeed, there is a fairly dark shadow on the ground that humans often ignore shadows. But the machine, unfortunately, doesn't ignore things. It sees everything. So the question is, can we now bring in knowledge? And it turns out we can, and this is what I did together with Stan Osha, one of the pioneers of the level set method, and with Stefano Suato. I basically said we want to infer this level set function given the input image, and then we can use this Bayesian formula to determine this posterior distribution. We can say it's the probability for the observation given the level set function times a prior on the level set function. And then the term in the down here is a constant, because we are maximizing with respect to phi to find the most likely level set function. Once you maximize this product of these two terms, you can equivalently minimize the negative logarithm of this product, and this gives you a sum of two terms, and indeed one is called the data term and one is called the regularizer. And so here you see the variational techniques reappear in a different, say, costume, namely the idea of minimizing a data term and a regularizer is actually equivalent to a maximum a posteriori inference. But what's interesting is this interpretation gives you an information of how you should choose the regularizer. The regularizer should always be the negative logarithm of your prior probability. How likely are different interpretations a priori? How likely are different 3D reconstructions? How likely are different segmentations? And so how can we define and compute likelihoods and probabilities? Well, one classical way is to revert to so-called density estimation techniques. This is stuff that was developed in the 50s and 60s by Akaike, by Rosenblatt, Partzen, and many others. Here is one of these density estimators. It's often called the kernel density estimator. It's just a sum of Gaussians centered around, in this case, each training sample. And in our case, the silhouettes are the training samples, so we train a shape prior on a set of silhouettes. Each silhouette is encoded by its sign distance function. This is the phi I. And then I say, how likely is a given distance function? Well, I just take the sum of these Gaussians that are centered at these silhouettes. And so once you project into 3D, indeed, each of these blue points that you see here is one silhouette. I took 100 such silhouettes, and this is an isoline of isosurface of constant probability. And so once you add this with a negative logarithm of this thing to the cost, it basically favors configurations that stay in the vicinity, in these yellow tubes, so to speak, in the vicinity of the training silhouettes. What does that look like? Here's the standard Chan-Wese method on the left. And here is the method where I replace the length prior by this shape prior. And so all of a sudden you get very nice segmentations of these images, frame by frame, such that each silhouette is similar to a human silhouette. It's not identical to the ones that I observed in the training, but it's similar in terms of this cost. And so this is nice. It seems to work. The approach actually generates human silhouettes. Anything that's not a human silhouette is very costly and will not emerge in the energy minimization. But if we make things a little bit more nasty, add a little bit of noise, we see that for the first 2 or 3 frames of the sequence it works, but then the algorithm gets stuck in a local minimum. This is typical for gradient descent optimization. These are all gradient descent minimizations, and you see this is a local minimum. So somehow there's something missing here. And what's crucially missing is that this is knowledge about how humans look like, the silhouettes, but not about the temporal correlation across different silhouettes. And obviously what makes a human a walking person is a very particular temporal pattern of silhouettes, one after the other. So the question is, can we learn that as well? That gets us to so-called dynamical models. So we take a training sequence, meaning a set of silhouettes where we also have a timestamp with each silhouette, and then we can train this. And so here's, I'll go through this a little bit more quickly. The first idea is that each silhouette is always represented with the embedding function, this level set function for silhouette I. And then for dimensionality reduction, I represent them with a principal component representation, meaning I have a mean embedding function and a set of eigenmodes. And so so basically that means I can then work with this vector of eigencoefficients. And so this is typically a vector that has, I don't know, 20 or 30 dimensions, depending on how accurate you want to encode the silhouette. And then I apply a dynamical model, a statistical dynamical model. And honestly, I don't know too much about time series analysis, so I actually went to the library, got a book about time series analysis. And if you open the book, basically on chapter 1 or 2, the first model that comes into the picture is the so-called autoregressive model. It's one of the simplest dynamical models. It basically states that this shape vector alpha at time t is nothing but a linear combination of the shape vectors at previous times, at times t minus 1, t minus 2. And for a model of order k, you would go to t minus k back in time. And then, so this is called a mean. These are called transition matrices, these coefficient matrices that model that linear combination. And then the thing that makes it a stochastic model, a model that is not fully deterministic, is that you add some Gaussian noise at each time. And the Gaussian noise has a certain covariance matrix. The fact is you can actually fit such a model to your training data. And easily determine, for example, by least squares, fitting the mean, the transition matrices, and the Gaussian noise parameters. And once you have these parameters, what you can do is you can simulate sequences of walking people. You can first simulate sequences of shape vectors. In fact, just by, this is called sampling from this Markov model. It basically means if you have shape vectors until time t minus 1, you can simply create that linear combination, add Gaussian noise, and you get the vector at time t. And with the vector at time t, you can recover with the PCA representation your embedding function. So I said, great, I trained the model, I simulated embedding functions, and here's what they look like. And you'll see in the beginning, they're really crappy. This is the first embedding function, it just wobbles around. At that point, I was going to throw things away and give up, but then I said, let me look at the 0 level. So I actually looked at the 0 level, and all of a sudden you see it's not just a random wobbly surface. No, you actually see walking silhouettes in that representation. So this is a dynamical model of shape that is based on an implicit representation, to my knowledge, the first implicit dynamical shape model. We can use that as a shape prior, and so for the sequence that I showed you before, we have to initialize. So on the first frame there's some overlap with the true segmentation, and then once we run the segmentation frame by frame, this is what we get. So you can see we can reliably track that person despite substantial noise. Since I actually simulated this sequence, I know what the ground truth is, and I could actually quantify the error. The error is just a few pixels, it's very small. In addition, I showed that if you have occlusions, like here, at some point the person is completely covered by this bar, still with the dynamical shape prior, you can actually track the person through very heavy noise and heavy occlusions. So it's a very strong model, so strong that if this was not the person walking, then it would hallucinate a walking person. I've also shown that in other experiments. 3D reconstruction. So 3D reconstruction is the problem I started my talk with, is one of many classical optimization problems, like segmentation is an optimization problem, 3D reconstruction. Optical flow is also a classical problem where variational methods are, to date, the leading techniques. These are a lot of pioneering works where people have proposed optimization and in particular variational methods to solve these kinds of problems. So for example, some of you may have heard the snakes, about the snakes of Kaswitkin-Terzopoulos, the Mumford-Shah model, the Gieman model, the Horn and Schunk optical flow model. So these are some of these papers have been cited 10,000, 20,000 times, 30,000 times. But they all have one thing in common, and that's all these cost functions are not convex. So coming back to the issue of convexity, it means once you do gradient descent, and most of these techniques do gradient descent, you will only find local minima. And the question is, how can we get around that? And so one research direction that we've been pushing a lot over the last, say, 7 years is how to move from an originally convex energy, a non-convex energy, to a convex one. Why is that useful? Obviously, once you have a convex energy, you can efficiently compute globally optimal configurations. The challenge, though, is if you start with something non-convex, how can you get it convex without sacrificing optimality in a way that you can ideally guarantee that the minimum of this problem is the same as the minimum of that problem? For 3D reconstruction, there are many ways to get 3D from images. The most popular one is the so-called photoconsistency consideration. The idea here is, I drew it here, is you can distinguish points like the green one from points like the red one based on projection into pairs of images. If you see the same color, this point is likely on the surface, whereas if you see different colors, like for points like the red one, this point is likely not on the surface because you're not actually looking at the same point. And that way you can, from comparing projections into the image, comparing the colors at these projections, you can have an indication of which points are likely on the object surface or not. And so you can associate with each voxel in that 3D space some value of photoconsistency, say in the interval 0 to 1. This is the function rho here. It's 0 for points like the green one, which are very photoconsistent, and more around 1 for points like the red one, which are not photoconsistent. And then once you have the photoconsistency, you can formalize 3D reconstruction as an optimization problem where you say find a surface S such that the photoconsistency, when summed up over all points of the surface, integrated over the surface, is as small as possible. This has been done. There are many variants of this in the literature. What is the key problem from an optimization perspective is that the class of cost functions that you get here are not convex in the space of surfaces. Meaning if you modify the surface and move around in that virtual 3D space, then depending on what values of rho you encounter, the energies will go up and down pretty much arbitrarily. So there's certainly no convex dependency in the context of perturbations of the surface. Nevertheless, we were able to show in 2009 that for this and similar classes of energies, one can compute provably optimal solutions by a technique called convex relaxation. And that means I can actually take a set of images, typically 20 or 30, calibrated images so I know where the camera was, and I can initialize randomly, like with a block, and then in this case, the gradient descent will actually give the optimal reconstruction. Optimal not in terms of the performance on benchmarks, but optimal with respect to the cost function that I considered. This is important. Often people say, why is that optimal? The ears, you know, are slightly blurry, etc. It's optimal for the cost that I considered. Meaning if someone gives me a better cost, I can compute a better solution. In fact, you see the resolution of the model is not super high, the fur details are missing, the eye details are missing, the ears are not very detailed. But one of the things we can do is we can compute the color on the surface. Here's how we do that when we do variational methods. This is, to my knowledge, the first time people have done it in this way. Although, from, you know, for someone from a variational community, this is the straightforward way to do it. What you do is you say, I want to find, given all the color images, II, from 1 through n, so there are n images, and given the surface S that are reconstructed, I want to compute the color T on the surface, an RGB value for each surface point. And what should that surface color be? The surface color should be such that once I project it into all the images, it should match the observation. More specifically, it should match the observation after blurring and downsampling, because this is what digital cameras do. Automatically get a certain blurring, and then the digital camera will downsample it to pixels. And so we can actually model the degradation that the digital camera applies in this cost function and say, find a texture T such that after blurring and downsampling, it matches the observation. Beta I is just the inverse of the projection here. So the aim is to find a coloring of the surface that is actually higher resolution than the input images. And this is in the literature called super resolution. It's been done a lot, but to my knowledge, this is the first super resolution texturing for curved geometries for 3D reconstruction. And then you saw, I skipped that, but you see there's a total variation here as a regularizer. So the usual regularizer that we use in most of the, in at least many of our papers. The only thing that makes it not fully trivial here is that this is the gradient when moving along the surface. So it's not the Euclidean gradient, but the gradient on the surface. I'll not go too much into detail of how we solve it. One thing that's important is this is a convex variational problem, because it's a quadratic data term, and total variation is also convex. And you see this is the textured bunny that we can recover. And I have the bunny on my table. It's sitting on my table. It's been there for years now. And I cannot distinguish that video from the original bunny, which tells you that with camera-based techniques, we are now at a level where we can reconstruct the world at a level of precision that fools the eye. And here's the really hard test of a super resolution approach. This is a zoom in on one of the input images, and they all have that kind of resolution. So you see they're all pixely like that. This is the texture that our approach computes. And you can see substantial improvements. This is important in any super resolution approach. You know, as the name indicates, you want to go beyond the resolution of your input images. Here we do. Typically here again, audiences are not blown away because we have CSI Miami, we have CSI New York, we have all these crime scene shows. I'm sure you've seen some of these series. In most of these, there is some sequel where the bad guy's license plate is in an image and it's very, you know, low resolution and pixely, and then the department of the like the police department, the head of the department says to the techie, "Can you zoom in?" And I don't know, have you seen these sequels? I'm sure you have. Typically, then the techie says, "Of course," and then he hits a button and it zooms and everything gets super sharp. And when I watch these, I always think, man, I wish I had that algorithm on my computer. Of course, we know it doesn't work. You cannot hallucinate details that are not there. So the question is, why does it work here? The main difference is that we don't have one such low resolution sampled version of the high resolution world, but we have multiple with slightly different discretization. And by exploiting the redundancy of having multiple low resolution observations, we can generate one high resolution version. We can, it means you have to do it properly. The variational approach seems to me the most natural way to do it. I'll go a little faster for time reasons. We showed that you can also impose silhouette consistency as a convex constraint in this framework, meaning we can recover geometries that are provably silhouette consistent, in the sense that if I take the 3D model and project it into each image, it perfectly matches the silhouette in the image. And that way we can preserve fine-scale structures like the sword here or the hammer. And so we get reconstructions. I would say if you want the most accurate reconstruction, take a laser scanner and scan the object. But there are many reasons why we don't want to use laser scanners. I think I'll skip the technicalities and come to the main part. Sorry about that, but I'm a bit running out of time. This is one short comment, maybe for those interested. You can go through the slides. This is a primal dual algorithm, which actually is faster than a gradient descent and has many favorable properties over the gradient descent. And it's a technique that's become very popular to minimize arbitrary convex cost functions. So, with this technique, we can recover 3D structures. Like here, we walked around some object in a museum, took photographs, and this is the reconstruction that we computed. Again, with a laser scanner, you would still get a more accurate reconstruction, but laser scanners are heavy. Laser scanners are expensive. They're not omnipresent. And here's something where I believe you could not do it with a laser scanner. This is sequences that were recorded in Edmond Boyer's lab in Grenoble. They have, at the time, 16, now actually 64, synchronized cameras that film this action. And we can reconstruct that action in time. For every time step, we can get a 3D model of the action. And this is something which I believe could never be done with a laser scanner, because it has to scan point by point or line by line. Cameras just get a much denser image data, measurement data. And so at some point you can then also back project the textures onto the objects, and what you get is what's often called free viewpoint television. And I believe this may be one of the futures of television, where you can see an action like this one from vantage points where there was never a camera to look at it. And you can, once you have a 3D model and the textures, you can do so many things. You can change viewpoint, zoom in and out. You can change illumination. You can change surface properties, reflectance properties, textures, everything, because you have a complete model. And here, to give you one last example, the resolution of these reconstructions is so high that we can recover the entire rope of a rope jumping girl completely just from the images. And I must admit, when I saw these reconstructions, I didn't actually believe my eyes. This is work by my student Martin Oswald. I didn't think it was possible from camera images to get such fine-scale details, but it turns out you can do it. Or he could do it, let's say. So to summarize, I talked about variational methods, gave you some of the basic ideas behind them, in particular the Euler-Lagrange equation. I showed you how you can relate this to statistical inference and how you can bring in prior knowledge about the world we live in. I showed how you can do 3D reconstruction with variational methods, how you can use compute high resolution and super resolution textures of 3D objects using these variational approaches, how you can do 3D reconstruction with silhouette consistency, and lastly I showed you that you can recover actions over time. Thank you very much for your listening.